Good evening everyone, welcome to Gate Academy Global. If my audio and video is clear, then just confirm me. Just confirm me both audio and video are clear or not. Rajesh, good evening Rajesh, and Srinu, good evening Srinu. Just confirm me audio and video, everything is clear or not. So today again I will continue. Sampling theorem, and I will discuss some number of problems from the sampling theorem also. Okay, just confirm me everything is fine or not. So in today's session, in last session already we have seen this thing. Just I will recall and I will continue. Okay, everything is perfect. Okay, so in last class, that just what we have seen. Suppose we have a signal. You can say this is a message signal. Either you can write MT or you can write by XT. Okay, now here what was our target? What was our target? Again I am going to write. Suppose we have one signal XT and this signal is passed from one switch, and this switch is logically called, you can say sample and hold circuit. Then again what we have to do, again we will do here analog to digital converter. This is not our concern right now. What is the our concern part? This sample and hold circuit. So here what should we speed up this switch? This thing we have to find out. And what will be the speed of this switch? You can say this switch is going to be closed in every TS second. This switch is going to be closed in every TS second. So what we have to find out? What will be the maximum TS? What will be the TS maximum? This thing we have to find out. If you will press more number of times than required, that will be good. But you cannot go with the less number. So we have to just find out how many samples you have to collect. From this message so that it can be recovered. So here we are going to write this is sample signal XST. So what is our target in this signal and system part? This part, sample and hold circuit, and this analog to digital converter you studied in, if you are from electrical in measurement, and if you are from electronics or electrical, you also studied the A to D converter in digital circuit, and some electronic student also study in communication system. Okay, so in many subjects you studied this part. So this part is the very important thing. What should be the maximum TS so that signal can be recovered? What was our target? Our target was to find out this TS. Now right now we don't know. This TXT message signal can be anything, and this cannot be direct message. This message, or you can say this is one signal, and also you can collect this signal from any system. So right now we don't know from where we are getting this XT, but if you will get this XT and XST is required, what will be the maximum TS here? This thing we have to find out. This is the sampling theorem. Clear this thing? Now clear? So in last class already we have discussed, if this is the message signal XT, just we assume the Fourier transform of this message signal is like this. Now one student are asking, sir, why we considered this as a triangle form? Generally we will write message signal Fourier transform in this form. Why? And what do you mean by this exactly? This is very important thing. Maybe communication system student know very well why we represent message signal in this form. Why? What was the reason? Right now we don't know about this signal. Suppose I am assuming this XT is my voice. So voice signal range generally from 0 to, or you can say 300 to 3.5 kilohertz. This is the actual range of voice signal. Okay, now if I will ask you what is the frequency of my voice, so this is not a single quantity, because my tone is going to fluctuate, my speed is going to change, so my voice is not a constant. So means my frequency is not a constant. Clear this thing? So but my voice signal frequency is in between 300 to 3.5 kilohertz, means 3.00 hertz. Clear? So suppose I don't know I don't know about this signal. Just I assume this xt signal frequency can start from zero, and the frequency can end till fm, and the frequency of xt can be any value, between 0 to fm, So this signal is not a single frequency component. This signal contains many number of frequency in between 0 to fm hertz. Clear this thing? This is not a signal containing single frequency component. If you are considering single sinusoidal or single cosinusoidal, that is only single frequency component. We have studied in Fourier series. If you have a square wave, in square wave you will get one frequency component, and harmonics of that many number of frequency components you will get. Similarly, right now we don't know the signal. Suppose if you are considering this is a voice signal, or you can assume this is a video signal, or you can assume this is a audio signal. Getting? So this will be the lowest frequency and this will be the highest frequency of this signal. Clear thing? Now the second question, sir, why we represent in this way? This is just protocol. We don't have here interested in this shape. We are only interested in this width. So this shape can be anything. You can also draw this shape as a square wave. But why? Generally we represent this as a triangle form. What is the reason of this triangle? Representation? So again I want to tell you, voice signal, suppose you can consider my voice. So if I will say loudly, speed will be decreases, and if I will say speedily, my loudness will be decreases. So this triangle generally we use for audio and speech signal, or you can say voice signal. This is generally used for audio and voice signal. Now what can I say? If you will increase the frequency, then amplitude will go down. But this is valid only for the audio and voice signal. This is not valid for the video signal. Getting this thing? So generally this is the standard protocol. All the engineers or all the writers generally use this, because we started any communication system from the voice or audio signal. So that's why this protocol generally we follow. Getting this thing? So I hope this thing is clear to all of you. Getting this thing? Okay. Now, so just I assume this is the xt signal and this is the Fourier transform of this xt. Clear this thing? So here right now we don't know how many frequency are containing this xt, but by this Fourier transform we can say this xt are containing frequency between 0 to fm, not a single frequency, many frequencies I can say containing frequencies between 0 to fm. Clear this thing? Now, so how we can convert this sample signal? So if you will pass this signal from the one switch, or you can say sample and hold circuit, you will get sample signal. And mathematically, how we can write this XST? We can assume this signal, if you will multiply with the impulse train, you will get the sample signal. So this is our assumption. Clear this thing? Now, so now my derivation is going to start. Okay, so here we have three parameter. Or one more thing I want to tell you here. Here three assumption can be possible. One will be the ideal sampling. Second one will be the ideal sampling is also called impulse sampling. So if you will assume CT as a impulse function, impulse train, this is ideal or impulse sampling. If you will consider this as a small pulse, this will be called pulse sampling or natural sampling. Again, if you will consider here pulse, but the pulse output you will get a flat top. This output will not be a varying during the pulse width. That is called the flat top sampling. We are interested in only here impulse sampling. Clear the thing? So now we have to study here only impulse sampling. So which parameter is our target? This is the your message signal, and this you have to multiply you have to multiply this signal with that C of t, you can say impulse train, and here output you will get here excess of t. Clear? See, you can also write, and what will be the excess? This is small excess t, this is excess of t. Clear? What you can write excess t, xt multiply, this is multiply ct. In Fourier transform you can also write, this is, you can say this is cf or c omega or c of z omega, you can write in any form, and this is nothing but xf, or you can say x omega, or you can also say xj omega. What will be this output? So here xs of f will be equal to, in terms of frequency I am going to write, this will be nothing but xf, this will be convolution with cf, So first what you have to find out, you have to find out Fourier transform of this ct. You have to find out Fourier transform of this ct. You have to find out Fourier transform of this ct means cf. What will be the cf? So what will be the Fourier transform? But before going to start this Fourier transform, first you have to write this signal mathematically. What was our target? I want this signal mathematical representation. This was our target. So first you have to write this signal mathematically. So ct, first student can write in this way, del t minus k times of ts, can I write? And this is the summation, k is equal to minus infinite to infinite, can I write? One student can write in this way, but I am not interested in it. I am interested in what is the Fourier series representation of this ct. So what is the Fourier series representation of this ct is equal to, this is summation ck e raised to power jk 2 pi k times of f naught. Here f naught will find out, f naught into t, and this is from k is equal to minus infinite to infinite. This is the Fourier series, exponential Fourier series. You can also find out here trigonometric Fourier series. This is a even function or odd function. You can say this is a even function. So trigonometric Fourier series also you can find out, anything you can find out. Okay, now so I am interested in here exponential Fourier series. So what will be the ck? ck will be 1 upon time period. I am considering from here to here, minus ts by 2 to ts by 2. So what is the duration of one period, that is ts, minus ts by 2 to ts by 2. What is the signal? This signal is, you can write 1 into del t. So you can write this is del t into e raised to power, this is minus j 2 pi k into f naught t dt. Can I write? What will be the f naught here? F naught, can I write? What is the f naught? What is the time period of this? You can say ts. So f naught will be 1 upon ts. Can I write? Or f naught you can say sampling frequency fs. So just you can replace f naught to fs. Here you can apply the property del t multiply any function, that function will be at 0. So e raised to power this t will be replaced by 0. So del t, area under the del t is 1. So what will be the ck? ck we are getting 1 by ts. Now you can put the ck here. So here I am going to write what will be the ct. ct we are getting here, ck is 1 upon ts, and this is independent of k. This is very important thing. So can I write this 1 by ts? Can I take it out? Yes. And this is summation of minus infinite to infinite e raised to power jk 2 pi k f naught t. So can I write this is summation of e raised to power jk 2 pi k, f naught is nothing but fs. Can I write fs into t? This is the ct. So we have two representation of ct, and what is the limit here? K is equal to from minus infinite to infinite. So we have two representation of ct here. We have two representation of ct here. Ready? I am interested in this one. So just you should remember first, always you should write this signal by the Fourier series mathematical representation. Always. Now clear? What will be this Fourier transform? Clear this function? Can I remove this? So ct we have already find out. So now I am interested in here, what is the Fourier transform of this? So, and directly you should remember, after this Fourier transform, graphically we will remember, what will be this Fourier transform. So, this Fourier transform CF is equal to 1 upon Ts is constant quantity, e raised to power j theta, or you can say e raised to power j k 2 pi k fs into t. This whole term you can say one constant into t multiply 1. So, what is the Fourier transform of 1? Del f, or you can also say 2 pi del omega. It's on you. Okay. Now, this thing also you can write in terms of omega. What you can write? Ct is equal to 1 upon Ts summation of k is equal to minus infinite to infinite 2 pi fs. I can write omega s. So, e raised to power j k omega s into t. Clear? So, you can also write this in terms of omega s. Now, one Fourier transform is either del f or 2 pi del omega. So, what will be the Fourier transform of e raised to power j k 2 pi, sorry, this is only 1k, na? This is only 1k, please. E raised to power j 2 pi k fs into t. E raised to power j 2 pi k fs into t into 1. What is the Fourier transform of this? What is the Fourier transform of this? This is the shifting property. Which shifting property? Frequency shifting property. And this is positive. So, what you will get? Negative term. So, what you will get here? Del f minus, how much this is j 2 pi k fs. So, how much you are going to shift? K fs. So, del f minus k times of fs. Clear the thing? If this is plus, this will be minus in terms of omega. In terms of omega, what you will get? E raised to power j, this is k omega s into t into 1. What you can write? 2 pi del omega minus omega s. So now it's your choice in which form you want to write. I am interested in always frequency term f, but examiner generally interested in omega term. Clear? In Fourier transform, already I tell you, you should make a table and all the Fourier transform properties you should write in terms of frequency as well as in terms of omega. But you have to follow one. Clear this? So, just way to find out this. Now, if I will put here 1 by Ts and summation, it will not be affected to right sided. So, what will be the Fourier transform of 1 upon Ts summation k is equal to minus infinite to infinite e raised to power j 2 pi k into fs into t. What is this Fourier transform? You will get 1 upon Ts, this is summation k is equal to minus infinite to infinite del f minus k times of fs. What will be in omega? What will be in omega domain? Omega is again very important. Okay, now what will be in omega domain? Omega domain, this will be same 1 upon Ts summation k is equal to minus infinite to infinite. What you will get here? 2 pi del omega minus omega s. 2 pi del omega minus omega s. Clear? And what is this value? This is nothing but Fourier transform of it is CF. So, can I write this is CF? Or you can say this is C omega. This is C omega. C omega is this one, and you can say this is CT. Sorry, this is CF. This is CF. And this is, you can say, this quantity is C of omega. Can I write? Now, graphical, we should know this thing. We should know this graphically. Getting? Graphically. So, how we can represent graphically this CF? How we can represent? Just you have to concentrate here. You have to concentrate on this Fourier series representation first. Then you have to find out Fourier transform of this CT. Clear this thing? You don't write this CT in terms of shifting del function. No. Clear this thing? Now, so can we plot this CF? Yes, easily we can plot. So what will be the CF? This is frequency domain and this is C of f. So what will be the CF here? This is the CF. 1 upon Ts and this is the shifting del. So again you are getting del, you can say impulse train. Fourier transform is again a impulse train. Directly you should remember this word. impulse train in time domain and impulse train in frequency domain. Always. So if time domain in impulse train, then in frequency domain again impulse train. But some changes. What changes you will get? This is the frequency. Then just you can plot this. Amplitude will be 1 by Ts. This is del 0, or you can say del f minus 0 del f. So here you will get first del f. Second you will get impulse here, next impulse here, next impulse here, and so on. In left sided also you will get one impulse here, one impulse here, one impulse here, and so on. What will be the amplitude? Amplitude is 1 upon Ts. So amplitude you can write all the amplitude is same, and this is 1 upon Ts. 1 upon Ts also you can say is equal to Fs. Also you can say Fs. Now this is 0. What will be the first interval? That is Fs. So this frequency is Fs. This frequency is 2Fs, 3Fs, and so on. This is minus Fs, minus 2Fs, and so on you can write. And you can also write here Fs is equal to 1 by Ts. But this is a frequency domain signal. So in frequency domain, generally you should write in terms of frequency also. So always you have to write in terms of frequency. Getting this thing? Now, so directly you should remember this Fourier transform is again a impulse train. Only what will be the difference? If this amplitude is 1, amplitude is area, if this is 1, here you will get 1 upon Ts, 1 upon Ts. If this was K, so here you will get K by Ts, but always Ct if you will draw, you will get always 1. So generally nobody will consider here K, but if here K will be present, just you have to write K by Ts. Getting this thing? And what will the frequency in every Fs, and Fs is sampling frequency. What will be the in omega domain? What will be the C omega? Clear this? Now, what will be the C omega here? Again, can we plot? This is C omega and this is omega. So in omega domain, again same. Again, everything is same. One impulse here, one impulse here, one impulse here, one impulse here, like this. Again, same impulse train, only there are some small difference. And generally students are getting wrong because of this only small difference in GATE exam. You have to concentrate. Here what is the magnitude? 2 pi by Ts. 2 pi by Ts. So this magnitude will be 2 pi by Ts. This is 0. This frequency is omega s, 2 omega s, 3 omega s, and so on. This is minus of omega s, minus of 2 omega s, and so on. Clear? So what is the actual difference? Here you can say this is sampling frequency in hertz. Again you can say here sampling frequency in radian, but amplitude is going to change. Already you know what is the impulse in a frequency domain and in omega domain. Already if you know this thing, del f is equal to 2 pi del omega. So by using also you can remember this. If here amplitude is Fs, so here amplitude will be 2 pi Fs. So here 2 pi will be multiplied. So just you should remember. Clear this thing? So if this signal you will get in GATE exam or in any exam, so directly you can plot this Fourier transform. You don't have to write the mathematical term. Clear this thing? You should remember impulse train Fourier transform is again a impulse train. Impulse train. Clear? So we have find out Fourier transform of this, and already we have Fourier transform of this, and then both Fourier transform will be convolved. Now just ask to you, Fourier transform, this Fourier transform, convolution with this is possible? Yes, easily possible, because you already know convolution with impulse is again a same signal. So easily we can do here. Fourier transform and convolution. Clear? So now, so what will be the Fourier transform of this sample signal? We are not going to write this mathematical term. We are directly going to plot this Fourier transform. Are you getting my point? What was our target? We want to write this mathematical term. But directly what we are getting right now? Fourier transform of this function. Clear? So just you should remember these things. impulse train Fourier transform is again a impulse train. Clear? Again a impulse train. Okay. Okay, you are asking, sir, in CT W KWS are, yeah, that is W minus WS, W minus KWS. No, W minus KWS. It will be W minus KWS. Okay. So what will be, again I am going to write, CF will be 1 upon TS summation of K is equal to minus infinite to infinite del F minus K times of Fs. Clear? And what will be in omega domain? C omega will be equal to, this is 2 pi by Ts summation of K is equal to minus infinite to infinite. This is del omega minus K times of omega s. Clear? And now you can plot this too. Getting? Now, what is the Fourier transform this excess? Okay, already you have plotted this. Okay, now, so again I am going to remove this part. Now, again I am going to remove this part, and again I am going to remove this part. Now, so suppose we have assumed this xt, and also we have assumed Fourier transform of this signal, Fourier transform of this, and this is suppose x of f, and this is f. Now, generally what we assume, this triangle, and what is this? Suppose this is maximum frequency of this signal, and this is 0, and always you will get mirror image. This is minus f. Clear the thing? And now suppose we are assuming this is a k. Suppose we are assuming amplitude of this is a k. Getting it? And already I explained you meaning of this. Why this is triangle, and what is the meaning of this 0 to fm? Because the signal can contain frequency between 0 to fm. Maximum frequency contained by this signal is fm. Clear? Now the second signal, this signal will multiply this not convolution with CT. So what we can say, this signal can convolve with CF. Can I write? And already you know the CF. What is the CF? Again I am going to plot here. This is the CF, and here this is impulse, here this is impulse, here this is impulse, here impulse, and here impulse. This is 0, and amplitude is 1 by Ts. This is Fs, this is 2 Fs, this is minus Fs, this is minus 2 Fs, and this is left sided till infinite and right sided till infinite. Now what will be convolution of this two? So separate convolution you can do. I am not going with mathematical convolution, I am going with graphical convolution, because graphical convolution is easier. So if you will convolve this with this part, this will convolve this with this with this with this. So in finite terms you have to just convolve. So what result you will get? So can I directly write here xt is equal to xst is equal to xt multiply ct, and what is the xs of f is nothing but xf convolution with cf. Directly can I find out this xf? Graphically. So directly I am going to find out graphically. I am not interested in here mathematical term. Mathematical term is not practically required here. So directly this convolution, this convolution with this 0th impulse. So if any signal convolve with del t, you will get same signal. So first part you will get as it is same. What will be this value? This is fm. This is 0. This is minus of fm. What will be this and this will be constant multiply k into 1 by ts. So this amplitude will be modified k by ts. You can also write this k into fs. Can I write? Now if this signal will convolve with this one, so this will be shift. How much shift? Fs shift. So same shape will be shift. How much it will shift? This will shift to fs. Similarly left sided it will shift like this. This is minus of fs. Can I write? If this signal is convolved with this, so this will be shift left side. Similarly till infinite you will get like this. What will be all the height? All the heights are same. This is minus of 2 fs and this is 2 fs. All the heights are same, and the value is k into fs or k by ts. Getting? So what we have find out? We have find out Fourier transform of this sampled signal. Fourier transform of this sampled signal. If I will ask you, bandwidth of this signal is infinite. Bandwidth of this signal is infinite. Clear? If I will ask you, bandwidth of this signal is infinite. Getting a thing? Now, so if you will find out sample signal of this signal XST, what you have to assume? We are assuming this signal is multiplying with impulse train, and just we have to find out Fourier transform of this XT. Now you will transmit this signal after analog to digital conversion. Then it will suppose transmit from one place to another place. Then again that signal will be converted from to digital to analog, and again you are receiving the same signal. And then what is your required signal? This is my required signal. So you have to pass this signal from the low pass filter, from the low pass filter. And low pass filter, what will be the characteristic of low pass filter? You can say this is a magnitude spectrum of low pass filter. What will be this cutoff frequency? We'll assume cutoff frequency is FM to minus FM. So this will be FM and this will be minus FM. Clear? What can be the amplitude of this? You can choose anything amplitude. What is your required? So amplitude can be modified or demodified easily by amplifier. Just I am assuming this as a 1, but you can assume this anything, what you want. Clear this thing? Now, if you will pass this signal from this low pass filter, what will be the result? Our result will be again original signal XT. Original signal XT, and you will get here Fourier transform of XT. This is FM, this is minus FM, and amplitude by amplifier, de-amplify or amplify, easily you can achieve the same quantity K. Just I am going to write here K. Ready? And this is nothing but again XF. This is nothing but here again XF. Clear? Ready? So what is your required term? I want this message signal again back. What should be the condition? These two should not be overlapped. What should be the condition? These two should not be overlapped. So here three cases can be possible. If this FM and this point, what will be this point? This point you can say Fs minus FM. What is this FM? If both are same. If this point is greater than this point, and third case, this point is less than this point, means both are getting overlap, both are separate, and both are at same point. Clear thing? So three cases can be possible here. So clear this thing? Now, so here three cases can be possible. So in which case you will get the output. And if you will get the inverse Fourier transform of this, you will get here XT. What is our requirement? I want this XT back. So first you are doing sampling. So if I will ask how you can do resampling, just a sample signal, if you will pass from the low pass filter or any filter, you will get return same signal. So if I want to write here, this is XT, just this is sample and hold circuit, and you are getting here excess of T. Again, if you will pass this from the filter, sometimes this can be band pass filter for band pass sampling, again you will get here XT signal. But in general real world, what we will do, after sample and hold circuit, we will convert analog to digital, and digital signal will be transmitted again at receiver side, digital to analog converter, and then again we should pass from the filter. Clear this point? Again we should pass from the filter. Clear this? Again we should pass from the filter. Ready? Now, so what will be the condition here? Here three cases can be possible. Case number one. What we can say, if this Fs is equal to twice of Fm. If Fs is equal to twice of Fm. So this both will be overlap. This is the minimum criteria. And this is called Nyquist rate. This is also called minimum sampling frequency. So if fs is equal to 2 fm, this is, you can say, minimum sampling frequency. Minimum sampling frequency. And this is called Nyquist rate. This is called Nyquist rate. This is called Nyquist rate. Clear? So fs is equal to 2 fm. If you want to write here what is the sampling interval or sampling time, so you are going to write this is the fs minimum is equal to 2 into fm. What will be the fs? You can write 1 by ts is equal to 2 fm. So what will be the ts? 1 upon 2 fm. And what will be the ts here? This is the maximum. This is the maximum. So initial I said you what can be the maximum sampling interval. If you can increase, if you can decrease, if you can collect more sample, that is good, but you cannot collect less sample. More sample can be good. So time, if you are going to reduce, that is good, but you cannot increase time beyond this limit. So what should be the speed of sampler? In simple way, if I will ask you, what should be the speed of sampler? That should be speed will be 1 upon 2 fm. Either these are faster than this, so this time will be less than this quantity. Either these are less than this quantity, so speed will be fast. So this will be the ts maximum. But generally we deal in this way. What is the sampling frequency? What is the sampling frequency? Minimum sampling frequency is this, and this is called the Nyquist rate. Okay, now the case 2. Now the case 2. What is the case 2? If fs is greater than 2 fm. If fs is greater than 2 fm means you will get here some gap. If you will get here some gap, then definitely if you will pass from the low pass filter, easily signal will be recovered. Again here signal will be recovered. Here signal will be recovered. Here again signal will be recovered. So again this is the okay for us. This is the okay for us. Now what is the case 3? Case 3, if you will consider fs is less than twice of fm, then signal will not recover. Signal will not recover. This is called aliasing effect. This is called aliasing effect. So this two will be overlap like this. This two will be overlap like this if fs will be less than 2 fm. So here we are interested generally in this part. We are interested in this part. So this we don't have to study. Okay, we are interested what can be the best sampling rate. What can be the best sampling rate? Clear this thing? So 3 cases can be possible. So if I will ask you what is the actual sampling frequency for any sample and hold circuit, what should be the sampling frequency? So we can say fs always should be greater than or equal to, greater is okay and equal is okay. So fs is greater than or equal to twice of fm. Twice of fm. Then what will be the minimum sampling frequency? Twice of fm. What is the fm here? What is the fm here? This is very important thing. Message signal can contain different frequencies. What can be the here fm? Maximum frequency component of message signal. Maximum frequency component of message signal. Maximum frequency component. If any signal contain 4 number of frequencies, what you have to consider? Maximum frequency. You have to consider maximum frequency. Clear this thing? Just you should remember, always sampling frequency should be greater than or equal to twice of highest frequency of the message signal. This is called Nyquist criteria. Nyquist criteria. Okay. What will be the minimum? fs will be equal to twice of fm. You can consider anything. Either you can choose fs is equal to 2 fm, or you can also choose fs is greater than 2 fm. Clear this thing? Now suppose, clear this? Now suppose, clear this? So this is the actual this is the actual Nyquist criteria. This is the actual Nyquist criteria. If you want to write this in terms of ts, so 1 upon ts, can I write greater than or equal to twice of fm? You can also write ts should be less than or equal to 1 upon twice of fm. 1 upon twice of fm. So suppose, for example, one example I am considering. One example I am considering, one signal is given xt. One signal is given xt, and what is the highest frequency component of this xt? Fm is given, for example, 1000 hertz. 1000 hertz. 1000 hertz Fm. So what will be the Ts? So Ts should be less than or equal to 1 upon 2 into 1000. This is 2000. This is nothing but 0.5 millisecond. This is nothing but 1 upon 2 means 0.5 milliseconds. So what should be the speed of sampler? What should be the speed of sampler? So Ts should be less than or equal to 0.5 millisecond. So speed, what can be the maximum speed of it? 0.5 millisecond. Speed can be means less, 0.2 millisecond, 0.3 millisecond, 0.4 millisecond, but you cannot consider here 0.6 millisecond. This is the important thing. How much fast sampler you have to require for the signal, which signal you want to transmit. Suppose if you want to transmit any signal, what should be the speed of that sampler? This is very, very important. You see, suppose you have very high frequency here. Suppose for example, this is in gigahertz. So if this is in gigahertz, then what should be the Ts? Ts will be in microsecond, or you can say nanosecond. So sampler speed will be fast. So can I say sampler speed is, so can I say sampler speed will be more for high frequency signal, can I say? So suppose if you want to transmit gigahertz signal, very fast sampler is required, Getting this thing? So I hope fundamental is very clear to all of you. Now this relation only you should know, sampling frequency should be greater than or equal to twice of the highest frequency component of the message signal. Highest frequency component of the message signal. Getting this thing? But this basic fundamental concept should be also clear. Okay? Now, clear this thing? Just confirm me. From where we are getting this relation? This thing is clear to all of you? Now, clear this? Okay? Now, just I want to ask you one question from here. One example I am going to consider, x of t is equal to 5 sine 2000 pi t. This thing is given, 5 sine 2000 pi t. 5 sine 2000 pi t. Clear? 5 sine 2000 pi t. What will be the minimum sampling frequency here? What will be the sampling frequency here? So here you can say a sine. First you have to find out how many frequency components there. Here you can say only single frequency. F1. What will be the F1 here? A sine you can write 2 pi f naught into t. So this you can relate with x is equal to a sine 2 pi into f1 into t. Can I relate? So what will be the f1 here? 2 pi if you will remove here 1000. So f1 you are getting, f1 is equal to 1000 hertz. And this is only single frequency, not minimum, not maximum, only single frequency component. So if you are considering this is a maximum frequency component, what should be the fs? Fs should be greater than or equal to twice of, you can write this is fm message signal, and this is only single frequency f1, twice of f1 or twice of fm. What answer you will get? 2000 hertz. And how you can write this? You don't say hertz here, you will say sample per second. So what is the fs? Fs should be greater than or equal to 2000 samples per second. This is the answer. So if you want to recover this signal perfectly, at least 2000 sample per second is required. So if you are considering 3000 sample, 4000, 5000, that is good. That is not bad. But if signal is going to recover, why you will take more sample? Why? If you will consider less sample, definitely signal will be not recovered. So we have three cases. One is the optimum, one is the more, and one is the less. less cannot be possible. If you will consider more, means you are wasting. If you are not getting anything extra, listen my point. If you will consider here 3000 sample, if you will consider 3000 sample, means you are wasting, because same signal will be recovered, not some specific non-spatial signal will be recovered, same signal will be recovered. So always, that's why we will use Nyquist criteria. Fs is equal to 2fm. Fs is equal to 2fm. Clear my point? Clear my point? If you will consider more, then you are wasting the bandwidth. You are wasting the bandwidth. Getting this thing? So optimum value generally we will use, because of the non-ideal filters. Sometime this will be more than 2000, slightly more than, sometime 1.2 times of the Nyquist rate. So sometime you will get in most of the previous year question, your sampling frequency is just 1.2 times of the Nyquist rate, 1.5 times of the Nyquist rate. They will not provide you 10 times of the Nyquist rate. Suppose this is 2000 sample per second is required. If you will collect 10,000 sample per second, you are wasting everything. You are wasting everything. Now here one magic will start. Now here one magic will start. Let's see. Now clear this? So generally we write like this. Now come on the fundamental side. Come on the fundamental. What is the Fourier transform of this xt? What is the Fourier transform of this xt? What is the Fourier transform of this xt? This is x of f and this is f. What is the sine Fourier transform? Magnitude spectrum you can plot. I can plot magnitude spectrum. What is the Fourier transform here? You will get one impulse here. You will get one impulse here. If this is sine or cos, both are same. What will be the frequency here? Sine 2 pi into fc or fm or f1. This is 1000. This will be minus of 1000. What will be this amplitude? 5 by 2 and 5 by 2. So this amplitude will be 5 by 2 and 5 by 2. So this is the Fourier transform of this one. Why you are getting impulse? Single impulse, because single frequency components are present. Only single frequency components are present. If here 3 frequency components are present of sine and cos, then 3 impulse will be present. Right now we consider single sine. So this is the your x of f. Now if you will consider here sampling frequency is 2 kilohertz, then what will be the Fourier transform of sampled signal? First term will be at same position. I am going to write in same position. This is 0, this is 1000, this is minus 1000, this is 5 by 2, this is 5 by 2. Now this whole signal will be shifted right, this whole signal will be shifted left. How much right? So this is 2000 if you are considering. So this is 0, you will get this 0 at 2000 point. This will be 2000 plus 1 3000, and this will be 2000 minus 1000. So again at 1000 you will get one more. So here this will be 5 by 2 plus 5 by 2, and in 2000 you will get 5 by 2 only. Again here this will be 5 by 2 plus 5 by 2, and here you will get at minus 2000. You will get 5 by 2. Again this will be again shifted. So again one more will be added here. So amplitude is not our concern. Our main concern is signal. Amplitude easily we can change by amplifier and deamplifier. Getting this thing? Now, so what is our required signal? Our required signal is this. Then again if you will pass this by the low pass filter, you will again receive the same signal. Now this is the low pass sampling. Can I say? Because you are using here low pass filter. Now suppose for example, if you will consider here this sampling frequency 1000 hertz, then what will happen? This is my question. If you will consider here sampling frequency 1000 hertz, then what will happen? Now we can assume. So here if I am going to assume, if sampling frequency fs, I am going to assume here 1000 hertz. then what will happen? What will be the excess of f? What will be the excess of f? Excess of f. So this whole signal will be shifted 1000 right, 1000 left, 1000 right, 1000 left, like this. So first signal will be in same position. Same position. This is 1000. This is minus of 1000. Okay. And this is 5 by 2. And this is 5 by 2. What will be the next signal? This will be shifted to 0. This will be shifted to 2000. This will be shifted to 0. This will be shifted to 0, like this. So again, this will be shifted to here. This will be shifted to left. This will be shifted to right. And this will be shifted to left. Similarly, every 1000 you will get the sample. This is minus 2000. Here again you will get 3000. Again you will get here at 3000. You will get like this. You will get like. But here you are again getting one sample here, one signal here. And this is not required. This is not required. Then if you will use here band pass filter, for example, if I will use here band pass filter, and this is the band pass filter. This is the band pass filter. So will you get your original signal? Yes, definitely your original signal will be again recovered. Again recovered. Original signal will be again recovered. So two types of sampling can be possible. Here you are not considering the Nyquist criteria. Less than Nyquist criteria, again sampling is possible. So three types of generally sampling we have to study. First, for the we don't know how many frequency components are present in the message signal. Then low pass sampling and band pass sampling, two sampling is possible. And third sampling you should remember for the sinusoidal or cosinusoidal. So for sinusoidal or cosinusoidal means for sine or cos, this Nyquist criteria is not useful. Is not useful. You can do also sampling with the lesser value. Getting this thing? So again I am going to draw. If this is the signal xt and if this is sample and hold circuit, you are getting here sample signal, and this is you are transmitting either analog to digital converter or in analog, that is your choice. And again if you are receiving here, and if you will pass from band pass filter, then again we can receive here xt. Again we can receive here xt. Getting this thing? So here two kinds of sampling can be possible. One will be low pass filter and one will be band pass filter. Now if I will ask you, this xt is a 5 sine 2000 pi t. If you will do here low pass filter, if you will use means low pass sampling, what will be the minimum fs? So here minimum fs should be equal to twice of this, means 2000 samples per second. 2000 samples per second. Clear this point? Now, but if you will use here, this is band pass filter you will use, and you can say band pass sampling. Then what should be the minimum fs? What should be the minimum fs? What should be the minimum fs? Anybody can tell me the answer? Anybody can tell me the answer? What should be the minimum fs here? Tell me. What should be the minimum fs? What should be the minimum fs here? Tell me. Anybody just tell me. Okay. Just tell me. I am waiting for your response. Yeah, Mr. Runs on DC sir, digital electronics course will be completed or some extra we will teach. Okay, we will make a plan. Right now we have considered or we have completed till the sequential circuit, and all the things I have, every topic we have touched. Later remaining topic we will try, but right now just we have completed that crash course part. Okay, just I have count that is total 40 hour of classes for the digital circuit. Okay, now just concentrate right now on signal and system. Anybody can say, if you will consider this signal as a band pass signal, if I will ask you this signal is a low pass signal or band pass signal, so here two answer can be possible. That is your choice. That is your choice. That is your choice. Clear this thing? Now, so if I will ask you single sine or cos are the low pass signal, or the low pass signal or band pass signal, anybody can say? So here this is 2000 samples per second. If you are assuming band pass signal, so this can be treated as either low pass signal or band pass, both you can treat. So if you will consider one more example, I am going to consider for this. If you are considering fs is equal to 500 hertz, suppose for example, suppose you are assuming here 100 hertz, suppose 100 hertz, then what will be the spectrum? What will be the spectrum of xs of f? Anybody can tell me what will be the spectrum? First signal will be in same position. This is 1000, this is minus 1000, and this is 0. What will be the next? So this will be shift 100 right, 100 left. So in 100 difference you will get everywhere. So in every 100 difference, here 10, here in every 100 difference you will get, in every 100 difference you will get, this will be 100, this will be minus 100, like this. In every 100 difference you will get. And again, if you will pass this by the band pass filter, again signal will be recovered, then again signal will be recovered, again signal will be recovered. So if you are assuming fs is equal to 100 samples per second, only 100 sample, again you can receive your original signal. So just you should remember, if you have sinusoidal or cosinusoidal, and if you are assuming this as a band pass filter, what will be the minimum sampling frequency? Any value. What can be the answer? Any value. It can be any value. But this filter is practical filter, so some width is required here. So we cannot assume here 1 hertz. We cannot assume. If ideal was 2000 sample per second, so in practical situation you can consider 50 sample per second. Again here reconstruction of signal is possible, but this will be only in the sinusoidal where Fourier transform is impulse, and single impulse. So if for any signal, if Fourier transform is impulse, then sampling frequency can be anything, but at least you have to assume minimum quantity. So just I am saying here minimum quantity is suppose 50 sample per second. Okay, so 50 sample per second. Also signal reconstruction or recover of the signal is possible. Getting this thing? And this is very important thing. Just confirm me this thing is clear. Okay, just confirm me this thing is clear. Okay, I will take some previous year question from this. So just be clear with this kind of signal. Now clear this. Now the second signal. If second example, next example, suppose if xt, and I am saying just xt is a signal is varied from 0 to 1000 hertz. This signal can be varied from 0 to 1000 hertz. What should be the minimum sampling frequency? So f has minimum sampling frequency will be equal to 2 into fm maximum is 1000. This is nothing but 2000 samples per second. So easily you can say. So examiner will not ask you this kind of question. Examiner are interested in this category of question. I will take some previous year question. Wait for this. So examiner are now interested in band pass sampling. Examiner are not interested in low pass sampling. So you can consider all the question in 2021-22 later gate exam. Always a question will be asked from the band pass sampling. I will start band pass sampling. Clear this thing? Now one more example I am going to consider. Next example, if x of t is equal to 5 sine 2000 pi t whole square, this whole square, like this whole square. So one thing you have to concentrate, always you have to separate first by the trigonometric, and you have to write always this signal in terms of x1t plus x2t plus x3t and so on. Always you have to write down in this way. This should be standard protocol. If xt having any square term like this, cube term like this. So first by the trigonometric, you have to do separate signal, and each and every signal contains single frequency component. So this xt contains suppose f1, this suppose f2, and this suppose f3, and so on. So just you to find out maximum. So what will be the f max? This is maximum from f1, f2, f3, and so on. Clear this point? If you are getting square, cube, anything, just by trigonometric you have to separate. So if you will separate this signal, xt, what you will get here? Sin square theta. So sin square theta you will get here. One is the DC term and one is the cos term, and that will be cos 2 theta. So what you will get here? One DC term and one cos 2 theta. So here second term frequency will be, this will be 4000. So this FM will be 2000. So DC frequency you can assume any frequency is possible in DC. Minimum you can assume that is a 0. So DC generally frequency you can assume 0 Hertz. Here you are getting sin square theta is 1 minus cos 2 theta by 2. So here you will get cos 2 theta. Cos 2 theta from cos 2 theta frequency will be double. So here what will be the FM? FM will be 2000 Hertz. What will be the sampling frequency? Should be greater than or equal to 2 into 2000. This is 4000 samples per second. 4000 samples per second. If you will assume low pass sampling. So this answer is valid for if you are assuming here low pass filter means low pass sampling. But if you will assume here band pass sampling, the things will be changed. Getting this thing? So just I am telling how to approach if you are getting a square term like this. Now the next example. If we will assume here x is equal to sinc function. Suppose sinc 1000t. Suppose sinc 1000t. What will be the Nyquist rate here? What will be the Nyquist rate or minimum sampling frequency here? To sinc t you can write, this is sine, this is pi into 1000t divided by pi into 1000t. If I will ask you what is the frequency, what is the bandwidth of sinc signal? What is the bandwidth of sinc signal? So here Fourier transform is required. So by using this you cannot solve. We can solve by using this also. First you can find out Fourier transform of sine and you can apply divide by t property. But directly we know this. What is the sinc 1000t Fourier transform? This Fourier transform is the pulse. If this is suppose x of t, then what will be the xf? Here area is 1 and this width is 1000. So this will be 500. This will be 0. This will be minus 500. And this width is 1000 and this area is 1. So height will be 1 upon 1000. Again I am telling you this is 1000. So this width will be 1000. What generally what student do here? This is 1 by 500. This is minus 1 by 500. Please don't do this thing. If this is 1000, so this width will be 1000. You don't write 1 upon 500 minus 1 upon 5. Don't. Please concentrate. Clear? If this is 1000, this width will be 1000. What will the bandwidth? Always we will consider right side. So what will be the bandwidth of this signal? Bandwidth of this signal is nothing but 500. How much? 500 Hertz. What is the bandwidth of this signal? Is 500 Hertz. What is the bandwidth of this signal? 500 Hertz. 500. Now I will ask you, this signal is a low pass signal or band pass signal, or can we treat both low pass and band pass both? Anybody can tell me? This signal you can treat low pass and band pass both. That is your choice. Because this Fourier transform, this thing is clear now. So what is the Fourier transform? Single sine or single cos? Fourier transform is magnitude spectrum of the Fourier transform. Here you are getting only this impulse, only. Where you are getting this impulse? This is 2000 pi t, means this 1000. this is 0, this is minus of 1000, minus of 1000, minus of 1000, getting? And this is your x of f, this is your x of f, clear? Now what is this Fourier transform? This complete from 0 to 500, but here no 0 to 1000, only at 1000. So this signal can be treated in two ways. Either you can treat this is a low pass signal, or you can also treat this is a band pass signal. This can be treated in two ways, but this cannot be treated as a band pass, because here frequency is starting from 0 and this is going to end at 500. Always this is a low pass signal. Just remember, this is always low pass signal, always low pass signal. You cannot treat this signal as a band pass. So here only one answer can be possible, only one answer can be possible. What is the highest frequency component? 500. So what will be the fs greater than or equal to 2 into maximum frequency? What is the maximum frequency? 500. So here 2 into 500, this is nothing but 1000 samples per second, This is the answer, this is the answer. So easily you can find out Nyquist rate or minimum sampling frequency for the sinc function. Here only one answer can be possible, only one answer can be possible, clear? You can treat this signal as a low pass also, and you can treat this signal as a band pass also, but this is only low pass signal, 0 to 500, clear? Now, so if I will write this question, x of t is equal to, suppose 5 sinc 1000t, or second question, x of t is equal to 5 sin 1000t, 1000t. Here, okay, this is sinc 1000t and this is sin 1000 pi t. Getting? What will be the sampling frequency? So here for the sinc, directly you can say sinc 1000, it means bandwidth will be 500, bandwidth will be 500. So what will be the Nyquist rate here? Fs will be greater than or equal to 1000 samples per second, samples per second, clear? But here what can be the answer? Sin 2 pi, here frequency is 500. So again here answer, Fs is greater than or equal to 1000 samples per second. So generally both the answer is same, sinc and sin, but you have to concentrate. Don't directly remember sinc is different, sin is different. How you can solve? You are already expert in the Fourier transform also. Okay, now, but if you will assume this low pass, but if you will assume this band pass, so what will be Fs are greater than or equal to any value? So here two answer is possible, but here only one answer is possible. Now second question. Clear this point? Clear this point, everyone? Now the second question. So can we solve sine or cos or sine square or any kind of sine? Okay, now the next question. If two different sine or cos is multiplied, suppose for example, so only here next game is trigonometric. Suppose x of t is given, for example, 5 sine 1000 pi t, multiply second cos 2000 pi t. So again remember my word, you have to write this in terms of x1t plus x2t. Then you have to find out maximum frequency component. Clear? Now here sin A cos B or cos A sin B you can apply. So here two frequency components you will get. One will be 3000 pi t, and second will be 2000 minus 1000 pi t. I am not interested in negative or in positive. I am interested in the value. So this is the maximum quantity. So 2 pi, this is the, what is the FM1 you can say here 1500, and what is the FM2 second message frequency you can say here 500. Can I say? So you can write 2 pi into 500, 2 pi into 1000, 1000 plus 500 and 1000 minus 500. Two frequency you will get 1500 and 500, which will be the maximum, this 1500. So what will be the Fs? So Fs will be greater than or equal to 2 into 1500 is equal to 3000 samples per second. Clear this? 3000 samples per second. Clear this? Again, remember my word. This answer is valid when you are considering low pass signal. This xt is a low pass signal. Now I am also interested in spectrum of this signal. What is the Fourier transform of this xt? I am going to draw Fourier transform of this xt is this xf, is this xf. Now here two components are present. One is at 1500 and second is at 500. So you will get one impulse at 1500 and second impulse at 500. Similarly here at minus 500 and here at minus of 1500, like this. Clear? Amplitude you can find out. Okay, now so here 4 impulse. Because of this 2 impulse and because of this 2 impulse, what will be the minimum sampling frequency? What will be the minimum sampling frequency? Suppose here I am going to assume sampling frequency is 1000. For example, actual sampling frequency you are getting 3000. Suppose I am assuming if fs is equal to 1000 samples per second. Suppose, then what will happen? Just you can draw the plot. What will be the spectrum for xs of f? What you will get? First signal at same position. This is 500, this is 1500, this is minus 500, this is 1500. This is 500, this is 1500, this is minus 500, this is minus 1500. If you are considering 1000, so this will come to here, okay. Now, and again this will come to 1000, then 1500, if this will be back at same position, this will be this side, everything will be same. This will be shifted to 1000 plus and 1000 minus. 1000 plus is 500, 1000 minus is 1500. Now this 1000 left sided, 1000 right sided, same magnitude will be only change. Now come to here, this will be 1000 here and this will be 1000 here. Again here you will get at 2500 minus of 2500. Again this will be shifted 1000 here and 1000 right. So again you will get at 2500. Clear this point? Now the next. Again this whole will be shifted. New signal will be shifted 1000 right, 1000 left. So every 1000 difference you will get the signal in every 1000. So in every 1000 you will get here samples like this. Now if you will pass from this low pass filter, and this cutoff frequency is 1500 Hz. This is low pass filter cutoff frequency. So will you recover original signal or not? This is my question. Will you recover original signal or not? Tell me the answer. Will we recover original signal? Yes, same signal will be recovered. If you are considering 1000 sample per second. But if you will consider 5 and again low pass filter, this is the magic. So if examiner will ask you question from the sinusoidal, means the signal which Fourier transform or which spectrum is impulse, you have to solve by logic only. You cannot solve by direct formula. Getting my point? Just you have to draw the spectrum and you have to think. Just you have to pass from the filters which they have provided you. Here we can also consider band pass filter. From here to here. But why you will consider? If you are getting from the low pass filter. So this you can also achieve by low pass filter. You can also achieve by band pass filter. So one student will do. So two kind of students. First student, if first student want to transmit this signal digitally, so how much sample he will collect? 3000. And second student are doing only 1000 sample. And in both you are receiving your original signal. Which will be the better? This can be the better. Getting this thing? So I hope this thing is clear to all of you. Getting? So here, if sampling frequency is 1000 sample per second, again low pass sampling is possible. Clear? So for sinusoidal or cosinusoidal, we don't have any direct logic. We have concept, and by using concept in GATE exam only you can solve the question. Getting this thing? Now the next example. If x of t, so can you solve? If sin square theta is given, if sin theta into cos theta, just by trigonometric you have to separate. Now, if suppose sinh square is given, suppose sinh square 1000 t, like this. So how you can solve this? Sinh square you can also write by sinh 1000 t multiply sinh 1000 t. Can I write? So if two sinks are given, if sinh square are given, you can also write in this way. Second, you can also write in this way. Sinh square, this sinh you can also write now sin pi into 1000 t divided by pi into 1000 t, and this whole square. Can I write? This whole square. Now you can also write sin square theta. You can also change. But I suggest you don't come to here. If sinh question, directly you should process from the sinh. You can also write in this way. If two sinks are multiplied, then what will be this Fourier transform? So can I write x of t is equal to sinh 1000 t multiply sinh 1000 t. Getting? What will be the Fourier transform of sinh 1000 t? Sinh 1000 t. What is the Fourier transform? This is a pulse. What will the pulse width? This will be minus 500, this will be 500, this will be 0, and this will be the frequency f. Now you have to concentrate. If you will write this in terms of omega, and if you will write here 500, everything will be wrong. That's why always I suggest you process with f, not process with omega. If you are processing with omega, you should be expert in that part. So frequency processing is easier. Generally frequency processing is easier. So in hertz you can directly write what will be the height. This amplitude is 1, means this area is 1. This will be 1 upon 1000. Now again same, this is sinh 1000 t. What is the Fourier transform? Again this is 500. This is minus 500. This is 1 upon 1000. Like this. Can I write? If these two are multiplied, this 2 will be the convolution, and already we are expert in convolution of two pulses. We are expert. If you have attended my classes, definitely you are expert. Not beginner or not moderate. You are expert in convolution of two pulses. So if these two are multiplied, this 2 will be convolutions. So easily you can also convolve. So if I will convolve, both the width is same. Many cases can be possible. We are interested in bandwidth. So this 500 plus 500, this will be 1000. This minus 500 minus 500, this will be minus of 1000. This is 0. You will get a triangle signal like this. So this will be the Fourier transform of this signal xf, and this is f. What will be the slope? 1 upon 1000, 1 upon 1000, 1 upon 1000 into 1000. This is the slope. 1 upon 1000 into 1000. This is the slope. Now you can easily find out the height. What will the height? Height will be, easily you can find out height. Slope is equal to y by x, and slope is given 1 upon 1000 into 1000. Y you have to find out, x is given 1000. Y will be 1 upon 1000. So this height will be 1 upon 1000. Clear this thing? So sinh square 1000 t spectrum is like this. Already if you have studied my Fourier transform classes, I tell in that point what is the Fourier transform of triangle. This is sinh square. That is sinh square. So directly if you remember, you can write. Now you should remember directly. What will be this 1000? If this is sinh square, the frequency will be double. What is the bandwidth here? Bandwidth, or you can say what is the FM, is equal to here 1000. Now again I will ask you, this is low pass or band pass? Low pass signal. This is low pass signal. So what will be the sampling frequency? Should be greater than or equal to 2 into FM. Highest frequency is 1000. So this is nothing but 2000 samples per second, 2000 sample per second. Clear? So if here sink square is given, sink A into sink B is given, can we solve? Yes, easily can we solve. Now the next question, next example. If x of t is given, sink 1000t, convolution with sink 2000t. Sink 1000t, convolution with sink 2000t. What will be this Nyquist rate? This kind of question many times in GATE exam has been asked. So how you can solve this Fourier transform? This Fourier transform you can write. This Fourier transform you can write. You can write like this. What will be this? 500. This will be minus 500. This is 0. I am not interested in magnitude. Here this is 1000. Here this is minus of 1000 and this is 0. Can I say? If these are convolution, so this will be multiplication. So what will be the multiplication of this two? Lower width you will get. If 500 to 1000, 0 multiply this, again you will get 0. What will be this two multiplication? Multiplication will be lower sided like this. So this will be 500, this will be minus 500. But amplitude will be, if this amplitude is A, this amplitude is B, this amplitude will be A dot B. Clear my point? Amplitude will be A dot B. What will be this highest frequency? 500. So what will be the answer here? What will be the answer here? Fs is greater than or equal to 2 into 500. That is nothing but Fs is greater than or equal to 1000 samples per second. 1000 samples per second. Getting my point? 1000 samples per second. 1000 samples per second. Clear this? So can we solve? We can solve sine square, sine cos, anything. First by trigonometric you have to separate, and second category of question you can get in terms of any kind of sink square, sink dot, sink convolution, sink, anything they can provide you. If you are expert in convolution and if you are expert in Fourier transform, we can solve anything here. We can solve anything here. Just confirm me, this thing is clear? Can we solve this kind of question? Easily can we solve? Now I am coming with a band pass sampling. If a band pass signal is given, then how we can solve? If a band pass signal is given, then how we can solve? Okay, just complete this. Now, okay, yes, I will tell you each and every query. Okay, right now for if sampling theorem, if you are getting any doubt, just ask me. Okay. Remaining every queries I will clear at the last of the today's session. Okay, now our next part is band pass sampling. Sometime generally what student feel this is a tougher part. No, wait, this is again a very easier thing. Now if I am considering one signal xt, and xt is a band pass signal. How you can say xt is a band pass signal? If I will provide you xt like this is not a band pass. Always band pass, low pass, high pass, band stop, you can say from the Fourier transform, means from the spectrum. So if this x of f, suppose xt is a band pass signal, and I am assuming suppose this is 80 and this is 120 hertz. This is frequency f. Okay. Now similarly here this spectrum is given in this way. This is minus 80 and minus 120. Now here I have not assumed triangle, because if you will assume triangle, sometime some conceptual mistakes can be done by us. That's why I assume here this kind of signal. Okay. Now clear? So suppose this is a band pass signal. This is a band pass signal. Clear? Now, so here which sampling you will do? If you will do low pass sampling, if you are considering this is a low pass signal, for example, so what is the FM? So FM you will assume here 120. So what will be the Nyquist rate or minimum sampling frequency? 2 into 120 is equal to 240 samples per second. But here we will not do low pass sampling. What we will do? We will do here band pass sampling. So here we will do band pass sampling. And this is basic mathematics only. This is not a conceptual things or anything new here. Only basic mathematics, school level mathematics is required. So suppose if we want to do band pass sampling, in low pass sampling, this will be shifted here. This will be shifted here. This space will be wasted. This space will be wastage. Now in band pass sampling, what we have to do? We will utilize this space also. We will utilize this space also. So here we will not assume 240 sample per second. We can also assume lesser sample per second. How? So we have to utilize this space. We have to utilize this space. Clear? Now how we can utilize? So just consider one side. I can say this is FH and I can say this is FL. So if you will consider this is low pass signal, then bandwidth will be 120 Hz. 120 Hz. But if you will consider this is a band pass signal, then what is the bandwidth? Bandwidth will be FH minus FL. FH minus FL, this is 120 minus 80 is equal to 40 Hz. Clear thing? If you will assume this is a low pass signal, bandwidth is 0 to 120. If you will assume this is a band pass signal, bandwidth is only this is a 40 Hz. Getting this thing? So here actual signal bandwidth is 40 Hz. So ideal, if in ideal case 40 into 2, 80. What is the sampling rate? Is 80 sample per second. But 80 sample per second always that will not be by 80 sample per second. This will not always satisfied. We have to check this will be satisfied or not. Getting this thing? So here if you are considering this is a band pass signal, what is the bandwidth? What is the bandwidth is equal to FH minus FL. FH minus FL is equal to 40 Hz. So what will be the FH? Sampling frequency will be greater than or equal to 2 into bandwidth. 2 into bandwidth. That should be. And this can be more than that. At least. But so here 80 Hz. So this FH can be greater than or equal to 80 Hz. But FH minimum will be equal to 80 Hz. This is the question mark. This is the actually question mark. We have to check this. This will satisfy the condition or not. So always this cannot be correct. Sometimes this can be wrong. Sometimes this can be wrong. If you will consider this is the bandwidth of the signal, so bandwidth multiplied 2, sometimes this can be wrong. Okay, I will take one example. Okay, so this thing we have to find out what will be the minimum sampling frequency. How we can find out? So we have to find out one parameter n. Just I assume one parameter. This parameter will say how many these samples can be present here. How many? So this width is 40. This width is 40. This width is 40. And this from 0 to 120. 0 to 120. So this can I write FH, highest frequency component, divided by bandwidth. Divide by bandwidth. It means how many this signal can be present here. Can be present here. So here if this is 40, here one more and here one more. 3 signal can be possible. So FH is 120. FH is 120 and bandwidth is 40. So here 3 signal can be possible. If this n is integer, means no space will be wastage. So I can say if n is equal to integer, then no bandwidth will be wastage. No bandwidth will be wasted. If this n is integer, suppose for example, if n you are getting 3.625, suppose you are getting, then again you have to consider n is equal to 3. Lowest integer, you have to consider lowest integer. We have to consider lowest integer. Why? I will tell you. Why you are considering, I will tell you. Okay. So first what we have to find out, how many this sample can be present here. How many? So from 0 to 120, this is 40. So 2 more can be present here. So you can utilize that space. Getting this thing? So first you have to find out how many more sample can be present here. So this one and this one and this two. So from 0 to 120, total 3 sample can be, or 3 spectrum can be present in that space. 3 spectrum. Getting this thing? So if n is an integer, directly you can write this answer is correct. This answer is correct. So if n is an integer, so f has will be greater than or equal to, or you can say f has minimum will be equal to what will be the answer? Fh, directly you can write Fh is 120 divided by 3 divided by n Fh by n. Fh is 120 divided by n, that is nothing but 120 by 3. It means in this space 3 samples can be present. So for one sample, how much bandwidth is required? For one sample, just wait, we have to correct that. No? For one sample, bandwidth is 40 required, 40. So for one sample, 40 is required and 2 times of that. So 2 multiply. You have to multiply because Nyquist said 2 times of Fm. This is your actually Fm. So this is your actually Fm. So Fh by n, you don't have to solve by this formula. By concept, you have to solve. So first you have to find out this n. If this is an integer, it means this is the Fm. Just you have to multiply by 2. Clear this point? If this is not integer, then what we have to do? Second example I am considering. Clear this? So for this, what will be the answer? 120 by 2 into 2 is nothing but sorry, this is a 120 by 3, 14 into 2, 80. This is 80 samples per second. 80 samples per second. It means what is the fs? Fs is 80 hertz. Now you can see this signal will be shifted 80 right, 80 left. This signal will be shifted 80 right, 80 left. Again 80 right, 80 left, 80 right, 80 left. If this signal will be shifted 80 this side, so this 80 will be at here. You will get this signal. Okay. Now, if this signal will be 80 this sided, so this 80 you will get like this. Now, clear? Now again this is 40 and this is minus 40. Getting? So this will be the 80 left sided. This will be 80 left sided. This will be 80 right sided. This will be 80 right sided. Getting? Now again this is shifted here. Again that will be 80. If this signal will be 80 shifted here, so minus 40 will be at 40. You will get same signal here like this. And this signal will be shifted here. You will get like this. So you will get this kind of signal. And then you have to pass from the band pass filter. Here we have to use band pass filter in this way. Here we have to use band pass filter in this way like that. So here we have to use band pass filter. So here no space are wasting. If this n is integer. So just we have to find out how many samples can be placed in vacant position. How many samples can be present in vacant position? Now by next example you will be more comfortable in this. Clear this thing? Now the second example. And by this example you will be more comfortable. Okay. Now the second example. Suppose we are considering a signal like this. Suppose this is 96 and suppose this is 104 like this. And suppose this is minus of 96 minus of 104 like this. This signal is given. And this is a Fourier transform of xt and this is magnitude spectrum. Suppose this is given. This is band pass signal or low pass signal? Band pass signal. So can I write this is a band pass signal? This is band pass signal. So here band pass sampling you have to do. What is the bandwidth here? This is 4. Bandwidth, this is 4 and 4. Okay, I am going to change the value. Suppose this is 94 and suppose this is 106. Okay, this is 94 and this is 106. Just change the value. Okay, now what is the bandwidth here? This is 6 and it's 106 and this is 6. This is 12. This bandwidth is 12 and here this is 12. If I will ask you what is the bandwidth of this signal, 12 hertz. So here bandwidth of this signal is 12 hertz. Bandwidth of this signal is 12 hertz. Clear this point? Now bandwidth of this signal is 12 hertz. Only by mathematics we can solve this band pass sampling. Okay. Now you have to find out how many this sample can be present here. This total length is 106. So here fh is equal to 106. Now if I will ask you how many this spectrum can be present here, how many spectrum, just you can divide. One spectrum require 12 hertz. So one parameter I am going to find out, n, you can say anything, n, k, l, m, anything you can say. Here fh by bandwidth. What is the fh? 106 by 12. You don't remember this fh bandwidth, by basic mathematics you can directly write. This is the 106, 1 is required 12, then how many spectrum will be present? 106 by 12. 106 by 12. So this will be integer or not? This will be integer or not? So 106 by 12, what you will get? 106 by 12. Exactly what value you will get? 8.833 something. What you will get? This is nothing but 8.833. You will get like this. This is integer or not? This is integer or not? Non-integer. Then it means there will be some space will be wastage. Some space will be wasted. So how much sample you can consider here? I will consider 8 samples. Or you can say 8 spectrum. You cannot consider 9 spectrum. If you will consider 9 spectrum, overlapping will be 100% occur. So how many spectrum I will consider? 8 spectrum. That's why in previous case I tell you, you have to consider minimum integer value, lowest integer value, not highest integer value. Getting? So lowest integer value is 8. So now by basic mathematically you can think here, total space is 106. One, you can see this is one diagram. You can see remember like this. This is one shape. And the total space is 106. How many this shape can be present here? So you are getting here 8.833 means 8 shape you can place there. So 8 shape we have to write, we have to place here, and this 8 shape we have to place here. So in between from 106 minus 2 plus, we have to place this 8 shape and this 8 shape. Clear my point? So from here to here, you have to place this 8 shape and this 8 shape. Some space will be wasted. Definitely some space will be wasted. If I will ask you how much space will be wasted, so from 0 to 106, so from 0 to 106, how many samples you are considering here? Total 8 sample. So 8 into 12. 8 into 12. 8 into 12 is the 96. Is the 96. And this is 106. So 10 unit, 10 hertz bandwidth is wastage. So can I say here 10 hertz will be wastage? Can I say 10 hertz will be wastage? That wastage, where you have to present that wastage? Getting? So first you have to find out this n. Now what can be the answer here? So answer can be slightly more than. This is 12 into 2, 24, slightly more than 24. Getting you see? So at least you can judge what can be the answer. So this bandwidth is 12 into 2 in the ideal case. But here always ideal case cannot be present, because this n always integer, you cannot find out. Sometime that will be more than that bandwidth or that sampling frequency. So ideal case sampling frequency you are getting 12 into 2, 24. Here you will get more than 24. How much more than 24? You have to find out. Getting? That value you have to write here. What will be the fs? Can I write? Fs will be greater than or equal to 2 into one signal bandwidth. One signal bandwidth or one spectrum bandwidth. So one spectrum ideal is 12, but some wastage is also present here. That wastage you have to consider here. How we can write the formula? How you can write the formula? So what you can say, from 0 to 106, how many samples? How many samples or how many spectrum? Total 8 spectrum. Total 8 spectrum. So from 0 to 106, a total 8 spectrum. Total 8 spectrum are present. So one spectrum required. One spectrum required how much bandwidth? So one spectrum bandwidth is equal to 106 by 8. 106 by 8. 106 by 8. So this will be the bandwidth of one spectrum. So what will be the 106 by 8? What will be the 106 by 8? What will be the 106 by 8? 106 by 8 will be 106 divided by 8. What you will get? 13.25. So this we are getting 13.25. 13.25. So what you have to find out? You have to find out one spectrum actual required bandwidth. Actual required bandwidth. Mathematically you have to find out. Getting my point? So one spectrum bandwidth is 13.25. So what will be the answer? 2 times of one spectrum bandwidth, and this is actual. This is actual. So what will be the answer? Fs is greater than or equal to, right? Now here you cannot put equal to, sorry, you cannot put greater than. This is Fs is equal to. This is Fs is equal to. Fs is equal to 2 into 13.25. This is nothing but 26.5 sample per second. Samples per second. This will be the answer. This will be the answer. 26.5 samples per second. 26.5 sample per second. Clear? Again I am telling you how we can find out. Again I am telling you how we can find out. Okay, how we can find out. So what you have to do? First you have to find out how many spectrum can be possible here. How many spectrum? Integer value. So if you are getting 8 point something, 9 point something, so 8 sample. So here 8 spectrum are present here. Getting 8 spectrum. So for one spectrum, how much bandwidth is required? Total bandwidth is 106 and 8 spectrum or 8 samples you can say, that is 13.25. So one signal or one spectrum bandwidth you have to find out, multiply by 2 is the sampling frequency. Is the sampling frequency. If suppose you will consider more than 26.5, suppose 27, everything will be wrong. So here you cannot consider just greater than that. No, that's why here I cannot put greater than or equal to. No, here this is equal to. Here this is equal to. What will be the next quantity? Next quantity again you have to find out. So what will be the second frequency? Second frequency will be multiply by 2. Multiply by 2. Second frequency will be multiply by 2. Clear this point? So can we solve? Can you solve? So any kind of question they can provide you. Just we have to find out what will be the sampling frequency. What will be the sampling frequency? Clear this thing? Clear this? Just we have to find out. Just confirm me. Okay, just confirm me. This sampling is clear or not? So here generally 3 kind of question we will ask. Generally one sinusoidal cases, one sync cases, and third one is the band pass sampling. So in band pass sampling you don't have to worry. Just you have to find out how many this shape can be present here. An integer number of shape you have to consider. So some wastage you will get here. So that wastage will be included in this bandwidth. In this bandwidth. So how you can find out? If this 8 shape are present here, so this total width divided by number of shapes. So you will get one shape required how much bandwidth. Just you have to find out. This is the ideal 12. Actually you have to find out. So ideal is given, actually you have to find out, and just actually you have to multiply by 2. You will get the answer. You will get the answer. Clear this? You will get the answer. Just confirm me this thing is clear or not. Just confirm me this thing is clear or not. Please confirm me. Okay. 1-2 question I am going to consider. Clear this? So one question in GATE 2020 has been asked. Just I am going to consider. Okay. One question I am going to consider. One question I am going to consider from here. Generally what student do here in this band pass sampling, student remember the formula. Generally what student do? Student remember formula. No, you don't remember the formula. Okay, just you have to apply the concept. Just you have to apply the concept. Now one more thing I want to tell you, in band pass sampling, for the your practice point of view, in band pass sampling, suppose you have find out sampling frequency, then for that sampling frequency just draw the spectrum. So same question, what was our previous question? Our previous question was like this, this was 104, this was 106, this was 94, and this was 96, this minus 94 minus 106. Here sampling frequency 26.5 hertz or 26.5 sample per seconds. Clear? So this is the sampling frequency. This is your homework. Just you have to plot this spectrum. Suppose this is x of f. You have to plot spectrum for the sample signal. You have to plot. So what you have to do? This will be shifted 26.5 right, left, again right. You have to shift this and left. Again this will be left, and then right. How much? 26.5, 26.5, and just you can see the shape. Just you can see the shape. In next 3-4 question, you have to do this thing. In next 3-4 question, you have to do these things. Clear? Getting this thing? You have to do these things. You have to do this thing. Clear? Getting? Okay. Now you have to do this thing in next 3-4 question. Okay. Now, so one question I am going to consider from GATE 2020. 2 question has been asked from the sampling. Okay, one more thing I want to tell you here. If you will ask me, sir, how many marks has been asked in GATE 2020? So in electronics branch, 8 marks. In electrical branch, 8 marks. And in IN branch, 7 marks. In GATE 2020. And from the sampling theorem, question has been asked from the IN branch, direct question from the sampling theorem. In this IN branch. In EC branch, sampling theorem, sampling plus discrete Fourier transform. Mixed question. And in electrical branch, they are not asked any question. So just you can consider in 3 branches, in 2 branches they are targeting, in one direct question, one you can say 50% question, 50% from the sampling, 50% from the DFT, and electrical branch they didn't ask. It means this is a approximate 50% weightage, 50% chances in GATE exam they can ask question from the sampling theorem. Okay, so if you will ask me, sir, how many probability, the question will definitely ask from the sampling theorem, that is 50% in your branch. So in every 1-2 years, every second year, 100% question will ask from the sampling theorem. Okay, just I am considering one question from GATE 2020 IN branch. Okay, just note down. Okay, now a sinusoidal of 10 kilohertz is sampled. A sinusoidal signal of 10 kilohertz. This signal is given and the sampling frequency is given here. Fs is equal to 15 samples per second. 15k samples per second. This is given. Now you can see here the sampling frequency is not twice of this. No. And this is a sinusoidal. Earlier I already tell you, generally examiner are targeting this category of question. Sinusoidal and less than twice of the maximum frequency. Because most of the student will do twice of the maximum frequency in sinusoidal. No, it can be also lesser than that. So here they have provided frequency of the sinusoidal and Fs 15,000 sample per second. Now the resulting signal is passed from, this signal is passed from low pass filter. This signal is passed from low pass filter, means they are considering this is a low pass sampling. They are doing low pass here. So they are just passing from the low pass filter, and this cutoff frequency is 25 kilohertz. This is minus 25 kilohertz. This is 0. Now they are asking the maximum frequency component at the output. Now the output you are getting here, output. Then maximum frequency component here. What is the maximum frequency component in the output. Clear? Maximum frequency component. One thing you should remember, if question will ask from the sinusoidal, always you have to solve by the spectrum. Remember my word, if the question will ask from the sinusoidal, always you should solve by the spectrum. Easily in 1-2 minutes you can solve anything. Just plot this signal. What is the spectrum of sinusoidal? 2 impulse, always 2 impulse. Here you will get at 10 kilo and here you will get at minus 10 kilo. And this is F. Can I say this is XF? If this is XT, what is the Fourier transform of this? Like this. Now, what is the sampling frequency? 15K. So, this will be shifted 15K right, 15K left, like this. So, what is the XS of F? What is the sampling signal Fourier transform? This will be shifted 15 right, 15 left. This will be shifted 15 left, you will get here at minus 5. This will be shifted here, you will get at 5K. Clear? Now, this will be shifted 15 right, 5, again 15, where you will get, this is 15 at 5, again 15, you will get at 20, you will get at 20K, again 15, and what is the filter? 25, so 25 greater than 25, I am not going to consider, okay. So, this you have to shift 15 right, here you will get at 5 plus 5, and that's again 15, 20. Then 35, then you will get here at 35. Can I write? So this you have shifted 15, 15, 15. Now again you have to shift this. This will be shifted here. This will be shifted here. Minus 5. Again minus 5 to again left sided. Again minus 20. Or you can say this mirror image. Minus 20K. Again you have to shift here. Minus of 30K. Minus of 35K. Like this. Clear? Now you have to pass okay, our sinusoidal is 10 kilohertz. Our sinusoidal signal is 10 kilohertz and sampling frequency is 15. Okay. Okay. So we have shift this right and we have shift this left. Now again you have to shift this signal right. So if you will shift this right, so 10 next signal you will get at 25. You will get at 25. And then again next 25, next 40. Next you will get here at 40. Here you will get at 40K. Again, this signal you will shift the left. So you will get at minus 25. You will get at here minus 25. And next you will get at 40. You will get at minus 40. Minus 40K. Clear this thing? Now you have to pass from the filter. You have to pass from the filter 25. You have to pass from the filter 25 like this. So how many frequency component you will get? 5, 20 and 25. So how many frequency component in output? 5 kilo, 20 kilo and 25 kilo. Getting this thing? What examiner asking? Maximum frequency component in the output. What will be the answer? 25 kilohertz. So this is the answer. This is numerical data. 25 kilohertz. This is the answer. This is the answer. Very, very simple thing. Now here, if you want, suppose if you want to back same signal, 10. Here 10 are not present. Here 10 are not present. Suppose if you want another frequency component, suppose you can also find out. Suppose if you want 20K, so just you have to pass 20K by the band pass filter. If you want 20 and 25 too, you have to pass this 2 from the band pass filter. So this is the magic. This is the magic. So by using one sinusoidal, you can create many sinusoidal. You can create many sinusoidal. If you want to create by this 10 kilohertz, 5, 20, 25. Easily you can create. Easily you can create. Just you have to sample this signal, and you have to pass from this low pass filter. Then you are getting here 3 signals, 5K, 20K, 25K. This is the magic. So many sinusoidal signal can be created by this sampling process. What you want, you can create. If you have 10 kilo, of sinusoidal. If you want 5 kilo, you can also create. If you want 20 kilo, you can also create. Not only lesser or greater, both can be created. Both can be created. You can see here, this is the 10 kilo or the original signal, and if output of this circuit, how many samples and how many signals you are getting? We are getting signals for 5 kilohertz, 20 kilohertz and 25 kilohertz. So this is very important topic. Generally examiner target this sinusoidal signal from the sampling. What you have to do? First thing, you have to just draw the spectrum. Just draw the spectrum. Then just you have to draw, Fs will be given. So just you have to shift right, left, right, left, right, left. But we have to concentrate. We have to concentrate. First you have to shift this. Left, left, sorry, right, 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 right. Then left, 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 left. Then again you can shift this. Right, 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 right. Then left, 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 left. Like this you have to do. Like this you have to do. Then you have to pass from the low pass filter. Then you have to pass from the low pass or band pass, any filter examiner, which examiner have provided you. Getting this thing? Clear this thing? So I hope this thing is clear to you. Generally examiner will target this. They are not interested in band pass sampling. Generally examiner are more interested in this sinusoidal samplings. Clear? So previous year question you should try to solve. Previous year question you should try to solve. Easily you can solve. Easily you can solve any question, I promise you. But you should be expert in Fourier transform. You should be expert in Fourier transform. Any question you can solve. Any question you can solve. Clear this thing? I hope everything is clear to all of you. I hope everything is clear to all of you. I hope everything is clear to all of you. Okay. So just again I will recall all the things in signal and system. We have studied basics of signals in very efficient way. Then Fourier series, periodicity of the signal, even and odd of the signal in complex signal and in real signal both. Then Fourier series, properties of some properties of the Fourier series. Then we have studied the fundamentals of the system, causality, stability, linear, LTI system, linear, time invariant, all the properties by input-output relation, by the impulse response of the system. And then we have studied Laplace transform, Z transform, Fourier transform, and then we have studied sampling theorem. Okay. Okay. Generally I focus on the fundamental parts. Because if fundamental will not clear, then you cannot solve any question in GATE exam. Now this is your duty. You have to try to solve previous year question. If you will get any doubt, just post over in my Telegram group. Okay, you can post any doubt. Okay, I will respond you. 100% I will respond you. Here's this point. So some topic is remaining, that is you can say discrete time Fourier transform, DFT. So DFT is only in electronics syllabus, discrete time Fourier transform and DFT, and some group delay and phase delay, that is also from the electronics branch only. Clear? So that part you have to do from the main channel, either main channel, or you can leave that part and or you can do by yourself. Okay, problem you can try to solve. If you have completed my whole signal syllabus in efficient way, I promise you approximate 70% mark, 70% you can get in GATE exam. So approximate 35 hour of classes we have conducted. Okay, so in 35 hour of classes, if you can solve 70% question, that is a big achievement. Clear? Getting? So I hope I know in signal and system many students are not much you can say energized or interested, because mainly I focus on the fundamental. This is my strategy. In digital generally I focus on each and everything, but in signal and system, because time was limited, mainly I focus on the fundamental. Now you should try to solve previous year question and you can ask me the doubt, and by this protocol I promise you, you can get good marks in GATE exam. Clear? Okay, so this session of signal and system today I am going to over. Okay, remaining topic if you will conduct, that will be separately provided to you. So this live classes of signal and system today I am going to end. Okay, getting this thing? So now it's your duty. You have to try to solve many number of questions from the signal and system. Clear? So if anybody have any doubt or any question, just ask me. If anybody have any doubt or any question, just ask me. Just ask me. Just ask me. Okay, just I am going to see your doubts. All the doubts is already cleared in today's class. Now, if anybody have any doubt, just ask me. Okay, so today's session I am going to stop. Okay, so later definitely again we will meet. Maybe with new subjects, or maybe with some new concepts, or maybe with some new strategy. So again we will meet. Okay, take care and wish you all the best. Okay, I am sure definitely you will get a good marks in GATE exam, definitely. Okay, so if you will get any doubt, just put over on my Telegram group. Okay, so thank you and bye bye. Okay, thank you very much.